Hello, my name is Audrey Mariani, and this is my Lab 1 analysis for constant velocity. The purpose of this lab was to create and compare a computational model of constant velocity with a model from a lab experiment using Glowscript technology and the Tracker app. The goal was to demonstrate the principles of Newton's second law by showing that no applied force means there will be constant velocity. In the experiment, we used a whiteboard marker that was the object that was being pushed. It was pushed along a meter stick as both the calibration tool and to ensure that it went in a straight line. We used the Tracker app to observe the position at each frame, and then we used Glowstrip to create a computational model of the experiment. Finally, we used Microsoft Excel in order to compare both data sets. Newton's second law states that an object's acceleration is dependent on the sum of all forces being applied. And you can see the derivations that we used in order to get the velocity update formula from Newton's second law, F equals ma. If there is no acceleration and velocity is constant, the net force on the object is equal to 0. We can see that by plugging in F is equal to 0 to the final equation down there, which results in final velocity equal initial velocity, meaning that it is constant throughout when F is equal to 0. Marker along a meter stick, as I said before. The potential issues in this data is that I apply initial force to the object and the object comes to a stop, meaning that there is friction being applied. This may have potential issues later on, but we'll get into that later. Using the Tracker app, the velocity was found to be negative 0.2369. The reason it's negative is because the marker is being pushed in the leftward direction, which means it's going towards negative x. We assume that in the time frame that I selected, the initial applied force is 0, and the friction is negligible. Here is the computational model, which shows the starter code that we used and then plugged our data into in order to model the constant velocity. We used the initial position and velocity vectors found from Tracker, and then from the other video. Then we set the net force equal to 0, which means that there will be no acceleration throughout it, so that keeps the constant velocity. And then we use the position update formula to create position graph based on the initial data that we had plugged in. So it estimated based on the change in position on each frame from velocity. Our computational model showed the same downward sloping graph that we found from the observed data. The difference is in this one we had a slightly different y and x intercept, which is due to some potential errors that we had earlier. Here is another representation of the data. On the left-hand side, you have the observed data, and on the right-hand side, you have the computational data. The observed is the orange line, and the computational is the blue. As you can see, the observed line has some variation and is not a perfectly straight line. This can be due to, like I said, the applied force, the friction at the bottom, or towards the end of the line, you can see how it starts to flatten out. That shows the negative acceleration, or the positive acceleration against the negative velocity, making it a flatter line. But overall, they do have the same slope and they are in the same general position, so while there was error, it was minimal. We know that velocity is the slope of the line due to the equation velocity is the derivative of position, and also just by reasoning, velocity is change in position over time, and the slope is change in the y over x. So since those are our variables, it all makes sense. What if the tracker axes were inverted and the x and the positive x and the negative x were flipped? If this were to happen, we would have actually gotten the graph that most people received in their experiment, and I put a picture in here of a general example of what the shape of the experiment would look like, or the chart would look like. It would just be a positive positive slope rather than a negative slope, because it would be traveling in the positive x direction rather than the negative x direction. Is it possible to estimate the forces being applied on the model? Well, due to our generally straight line, we can assume, or we can take away that the net force was 0 during at least a majority of it, other than the very start and the very end. This is confirmed by both the computational and the observation models. What we do know, however, is that there was friction, which caused the object to stop, and there was the initial applied force, which caused the object to start moving. So in the x direction, we may have possible forces on either end, but in the middle segment, which was the basis of where our data was taken from, it is generally 0. We also know that in the y direction, it is 0 because otherwise it would have moved either off or through the ground. This is because gravity and normal force cancel each other out, making sure that the object is on the ground. In conclusion, the computational model proves the general accuracy of the observed model due to the same velocity found and the same general graph. The object experienced a net force of 0 throughout this experiment, or throughout the middle section of the experiment, which once again is proven by the constant velocity. Thank you.